So our next speaker is Asmae Tafraouti from the East. And the title of her presentation is Microelectrical Discharge Machining, Effect of Physical and Electrical Parameters on Crater Size. So, Asmae?
Okay. Hello, everybody. I am Asmae Tafraouti, PhD student in the third year at the Lyon Institute of Nanotechnology, Devices for Earth and Environment team. I will present you a part of my work concerning the effect of some parameters on the machining performances. For this, I begin with the context and the goal of my work, then the machining techniques, and in the end, I will show you some results of my experimental study, and I will conclude with a review and outlook. ENL is a laboratory that is interested in research in the field of micro and nanotechnology and their applications. The Devices for Earth and Environment team is interested in the manufacture of microfluidic systems for different medical applications. The team has been interested in many technologies, particularly polymers for hot embossing techniques, which requires the manufacture of master models. Devices for Earth and Environment teams aims to use materials that have an industrial future. That's why it chose steel. The problem is steel cannot be machined by the usual microtechnology techniques. For that, the µEDM has been chosen. So the goal of my PhD is to form molds with machining resolution equal to 5 micrometers. To achieve this stage, it's necessary first to fabricate cylindrical micro tools with diameter up to 5 micrometers and with high aspect ratio in order to machine deep channels with a very good resolution. To achieve this resolution, it's necessary to find solution of this phenomenon, which is represented by random discharges. This leads to the obtention of craters with non-uniform sizes. For that, I did study on the different machining parameters in order to improve the process and manufacture crater with uniform size. In the machining domain, we find several techniques as mechanical cutting, laser beam machining, and hot embossing. The two first processes represent a risk of the distortion of the desired shape during the machining. However, hot embossing requires the use of the clean room, which is a little complicated in industry. For that, we have chosen the microelectrical discharge machining to manufacture master model on the steel workpieces. I present you now my experimental results. During machining, we use this bench, which is composed by AC circuits. The charging and discharging voltage across the capacitor depend on the physical conditions during plasma creation. The microtool electrode used during machining is made of tungsten because it has a high melting temperature, which reduces the wear rate of the microtool electrode during machining. In our experiments, we fabricate microtools by electrochemical etching. They are cylindrical with high aspect ratio, which help us to achieve high resolution during machining. While we use stainless steel for the workpiece electrode because it has a low melting temperature and low thermal diffusivity, which provides the diffusion of the discharge energy locally. Before starting the machining, we do this preliminary step to determine the initial gap between the two electrodes. First, we apply in air a voltage of 1 volt between the two electrodes. Then we move down the microtool electrode with a step of 1 micrometer until mechanical contact is detected. After that, we move up the microjoule electrode by a distance of 40 micrometers. For us, this distance represents the reference. Finally, we apply a voltage between the microjoule and the workpiece. The implosion of the plasma causes a local fusion of the material on the workpiece surface, forming small crater. In order to understand the effect of electrical parameters on the machining performances, we calculate the average discharges energy. In our estimation, we don't take in consideration the discharges where the current is under 50 milliampere because these discharges have low energy, just some nanojoule, and appear before the breakdown. We also calculate the removed volume. To do that, we use a profilometer in order to estimate the shape of the crater as shown in this figure. By following these steps, we have now the electrical breakdown for the different microjoule diameters as shown in this graph. The electrical breakdown is constant. It's equal to 6 volts per micrometer for the different microjoules diameter. This information is useful to determine the breakdown gap for different applied voltage. We also determine the average discharges energy according to the different microjoule diameters for an applied voltage of 25 volts, 50 volts, and 75 volts. We have seen that the average discharges energy don't depend on the microjoule diameter. It varies just according to the applied voltage. For an applied voltage of 25 volts, it's equal approximately to 8 microjoule. For 50 volts, it's around 15 microjoule, and for 75 volts, it's equal to 30 microjoule. Concerning the removed volume, it is identical for microjoules where the diameter is less than 125 micrometers, whatever the value of the applied voltage. In the case of microjoule diameter of 250 micrometers, the machined volume depends on the applied voltage. For an applied voltage of 25 volts, we have obtained just surface traces. So we have not been able to estimate the removed volume. However, for an applied voltage of 50 volts and 75 volts, the removed volume becomes significant. Based on all these results, we can conclude that the electrical breakdown is identical for the different microjoules diameter, that the average discharges energy doesn't depend on the microjoule diameter. It varies according to the applied voltage. Concerning the machine, the volume is in the same order for small diameter, regardless of the applied voltage. This result is useful in the choice of the suitable microjoule diameter depending on the machine phases. The microjoule with high diameters will be used during the roughing phase, where the removed volume is important, while small microjoules diameter will be used in the finishing phase in order to ensure the obtention of crater with less rough surface. This study was important to understand the effects of each machining parameters and be able to choose the optimal parameters for the drilling holes. Our outlook in this part is the characterization of the holes drilling by microelectrical discharge machining. This is an example of a hole obtained while using microjoule diameter of 250 micrometers and an applied voltage of 50 volts. If you have any question, I'm here to answer it and discuss with you my results. Thank you for your attention.
Thank you very much for your nice presentation. We have time for a few questions.
Yeah.
If not, I would like to ask you the depth of the hole? I mean, you mentioned 310 micrometers of diameter, but in depth?
For this example?
For the depth. Yeah, this is, for example, 109 micrometers of diameter.
Yeah, for this example, I have obtained the depth of 200 micrometers.
Okay, 200, okay. Thank you. If not more questions, thank you very much for your presentation, Asmae.
You're welcome.